Hello friends, myself Dr. Sachin Sarode. I welcome all of you. In this video, we will learn definition of greatest common divisor of two integers a and b and how we can express GCD of a and b as a linear combination of a and b. Before that, we will learn when an integer b is said to be divisible by an integer a. We will learn the definition. An integer b is said to be divisible by an integer a if there exists an integer c such that b equal to a into c and it is denoted by a divides b. Suppose you have two integer a and b, then b is said to be divisible by a and a is non-zero if there exists an integer c such that b equal to ac wholes. For example, suppose if you take b to be minus 15 and a to be 3, then there exists minus 5 such that minus 15 is equal to 3 into minus 5. Therefore, we say that 3 divides minus 15. Now take b to be minus 15 and a to be 2. We can observe that minus 15 is not divisible by 2. That is, 2 does not divide minus 15. Why? Since there does not exist any integer c such that minus 15 is equal to 2 into c. We have learned the division algorithm. By using the division algorithm, if we take b to be minus 15 and a to be 2, then we can have q as a minus 8 and r as a 1. We can write minus 15 equal to 2 into minus 8 plus 1. Here remainder is 1. Remainder is not 0. Therefore, 2 does not divide minus 15. But if we take minus 15 and 3, by using division algorithm, we can write minus 15 is equal to 3 into minus 5 plus 0. So here 0 is the remainder when minus 15 is divided by 3. Therefore, minus 15 is divisible by 3. Now we will learn these results. If a, b, c are any integer, moreover if a divides b and b is not equal to 0, then mod of a is less than equal to mod of b. Suppose you have two integer a and b. If a divides b and b is non-zero, then absolute value of a is less than equal to absolute value of b. I explain this result with example. If a is 2 and b is minus 26, we know 2 divides minus 26. Absolute value of 2 is 2 and absolute value of minus 26 is 26. Therefore, absolute value of 2 is less than equal to absolute value of minus 26. We have to prove this result. Suppose a divides b. By definition, there exists an integer c such that b equal to a into c. What we have, b is not equal to 0. We have assumed that b is not equal to 0. Therefore, we get c is not equal to 0. Why this? If c is equal to 0, then a into 0 is 0. But we have already taken b is non-zero. Therefore, c is non-zero. Now we will take the absolute value on both sides to this equation. B is equal to ac. Therefore, what we will get? Absolute value of b equal to absolute value of a into c. But we know absolute value of product of two integer is same as the product of absolute values of two integer. Therefore, mod of a into c is equal to mod of a into mod of c. C is non-zero. Therefore, absolute value of c is greater than or equal to 1. We know that absolute values are always greater than or equal to 0. and C is an integer. Therefore, absolute value of C must be greater than or equal to 1. Now we multiply this equation by mod of A on both sides. Therefore, we will get mod of A into mod of C is greater than or equal to mod of A. Hence, mod of B is equal to mod of A into mod of C. But mod of A into mod of C is greater than or equal to mod of A. That is, see here, mod of B is greater than or equal to mod of A. So I can write mod of A is less than or equal to mod of B. And that is we have to prove. Mod of A is less than or equal to mod of B. We will learn next result. If A divides B and A divides C, then A divides Bx plus Cy for arbitrary integers x and y. Arbitrary means what? Any. If we have A, B, C in integer and A divides B and A divides C, A divides both integer B and C, then A divides Bx plus Cy. Bx plus Cy means what? It is a linear combination of B and C. That is, A divides linear combination of B and C. I illustrate this result with taking some particular values. If A is 3, B is 6 and C is 12, then we know 3 divides 6 and 3 divides 12. Our condition is satisfied. Now, taking any integers x and y. Now, just illustrate, take x to be minus 2 and y to be 4. Then Bx plus Cy is what? Equal to, B is what? 6, x is what? Minus 2 plus C is what? 12 and y is what? 4. Therefore, Bx plus Cy we will get 6 into minus 2 minus 12 plus 12 into 4 48 minus 12 plus 48 is equal to 36. And we know 3 divides 36. We will prove these results now. What we have? A divides B and A divides C. So if A divides B and A divides C, by definition there exists an integer R and S such that B equal to AR and C is equal to AS. Take x and y be any integer, because we have to prove A divides Bx plus Cy for arbitrary integer. So take x and y as any integer and consider Bx plus Cy. Now take the value of B as AR, write down here AR into x, plus put the value of C as a AS into y. So we will get Bx plus Cy equal to ARX plus ASY. Now take A common from these two. Therefore we will get A into Rx plus Sy. Now R is integer, X is integer, therefore Rx is integer. S is integer, Y is integer, therefore Sy is integer, and sum of two integers is again integer, therefore Rx plus Sy is integer. What we have? Bx plus Cy equal to A into integer. So by definition of divisibility, A divides Bx plus Cy, and that is we have to prove here. A divides Bx plus Cy. Now we will learn the definition of greatest common divisor. If A and B are two given integer with at least one of them is not 0, the greatest common divisor of A and B is denoted by GCD A comma B and is the positive integer D satisfying first condition, D divides A and D divides B, and second condition, if C is any other integer such that C divides A and C divides B, then C is less than or equal to D. See here, I explain the definition of greatest common divisor. If you have two integer A and B, at least one of them is not 0. Why we have taken at least one of them is not 0? If both are 0, suppose both are 0, A is 0 and B is 0, then what happened? We know every integer divide 0. 100 divides 0. 100 zeros are 0. 200 also divides 0. Means any integer will divide A and B if A and B are both 0. And we could not find the greatest common divisor. See the meaning, greatest common divisor. We have to take all divisor of A and B. Then we have to take the common divisor of A and B, and among them we have to choose the greatest one. It is called the greatest common divisor. Therefore, at least one of them is not 0. Then the greatest common divisor of A and B is denoted by GCD of A and B, and it is an integer D such that D divides A and D divides B. And if any other integer C divides A and B, then that integer C is less than or equal to D. Okay, I explain definition with example. If we have to find GCD of 15 and 18, firstly we will factor 15. 15 can be factored as 3 into 5. Then we factor 18. 18 can be factored as 2 into 9. And again 9 can be factored as 3 into 3. Therefore 18 is factored as 2 into 3 into 3. We have to take the common factor. See here, 3 is here, 3 is here. So 3 is the common factor. Is there any other factor? No. Therefore 3 is the common factor and it is the greatest. Therefore 3 is the greatest common divisor of 15 and 18. See, if we have to find the greatest common divisor of minus 12 and 30, we will factor 12. Although we have to find the GCD of minus 12 and 30, we will take the factor of 12. 12 can be factorized as 2 into 6 and 6 can be factored as 2 into 3. Therefore, 12 is factored as 2 into 2 into 3. Also, 30 can be factored as 2 into 15 and 15 can be factored as 3 into 5. Therefore, 30 is factored as 2 into 3 into 5. Now, we have to take the common factor or common divisor. See here, 2 is a common divisor, 3 is also common divisor. So, I cannot say that 2 is the GCD or 3 is the GCD. Since 2 into 3 is what? 6 and 6 also divides 12 and 6 also divides 30. And is any another common factor is there? No. Therefore, the greatest common divisor of minus 12 and 30 is what? 6. Now, we will learn GCD of any two integers a and b can be written as a linear combination of a and b. We will learn this theorem. Given integer a and b, not both of which are 0, then there exist integers x and y such that GCD of a and b is equal to ax plus by. Here ax plus by is a linear combination of a and b. Means what this theorem says, if you have any two integer a and b, then we can find the GCD of a and b. Then GCD of a and b is a linear combination of a and b. There exist two integers x and y such that we can write GCD of a and b equal to a into x plus b into y. First we will prove this theorem. So consider a set S AU plus BV such that AU plus BV is strictly greater than 0, where u and v are integer. What is meaning of this set S? Set of all positive linear combination of a and b. Why we have taken this set S? See, we have to show GCD of a and b equal to linear combination of a and b. So here we have taken the linear combination of a and b, AU plus BV, such that u and v are integer. Again, we have already learned GCD is always positive. Therefore, we have taken AU plus BV is greater than 0. Therefore, what is the S? Set of all positive linear combination of a and b. Firstly, we will show that this S is non-empty. How we will show that? We will show it by computation method. Now what we have taken? We have taken any integer a and b, not both of which are 0. So consider a is not 0. Suppose a is not 0. Then integer mod of a, absolute value of a equal to au plus b into v belongs to yes. Why? See, here we have taken value of v as a 0 and value of u is depend on value of a. Suppose if a is positive, then we will take u as a 1. So mod of a will be equal to a and a is greater than 0, therefore a will be in yes. Suppose a is negative, then mod of a is equal to minus of a into, we will take u as a minus of 1. Therefore minus a into minus 1 will become a and mod of a is equal to a is again greater than 0. Therefore again mod of a will be in yes. Therefore the set yes is non-empty. Again I explain this. Suppose a is non-zero, then the integer mod of a is equal to au plus b0 belongs to yes. For value of u is equal to 1 or minus 1 according as a is positive or negative. If a is positive, then we will take u as a 1. If a is negative, then you will take u as a minus 1 and then mod of a is belongs to yes. Therefore yes is non-empty. Already we have learned the well ordering principle. What well ordering principle says? If we have taken yes is any non-empty set which is a subset of non-negative integer, then it contains a least element. So by well ordering principle, yes contains a least element. Say that element is d. Now d in yes, and yes contains a set of all positive linear combination of a and b. Therefore d is a linear combination of a and b. Therefore there exists an integer. X and y for which d is equal to ax plus by. See here, d is a linear combination of a and b. Now we claim that d is the GCD of a and b. Consider a and d. See, a is any integer and d is a linear combination of a and b and it is positive. So apply the division algorithm to a and d. Therefore there exists an integer q and r such that a equal to d into q plus r, where r is greater than or equal to 0 and less than d. Now we can write r as, see here, I just write dq to left hand side. So we will have r equal to a minus dq. Now we will put the value of d. This is equal to a as it is minus, now q in bracket value of d. What is value of d? Ax plus by. Now we will simplify this, a as it is. Now I will multiply this minus q to hold this bracket. So I will have minus qax minus qby. This is equal to, from this I will take a common. So a into 1 minus qx plus, now I will write down b into minus of qy. So what r becomes? R equal to a into 1 minus qx plus b into in bracket minus qy. That is, r is a linear combination of a and b. If r is strictly greater than 0, means if r is positive, then r will be in yes, because yes is what? Set of all linear combination of a and b and which are the positive. But r is less than d. From here r is less than d. So we got the contradiction. To d is the least element of yes. Already we have say that d is the least element of yes. So we don't have another element which is less than d. But we have here r is less than d, which is a contradiction. Therefore r must be a 0. And when r becomes as a 0, we will get A is equal to D into Q plus 0. That is A is equal to D into Q. And A is equal to D into Q, by definition of divisibility, D divides A. Similarly, the same method, by using the same method, we can show that D divides B. Therefore, D divides A, D divides B. Therefore, D is the common divisor of A and B. If C is any integer such that C divides A and C divides B, then C divides ax plus by. Already we have seen this. If C divides A and C divides B, then C divides a linear combination of A and B. That is, what is ax plus by? Ax plus by is what? D. Therefore, C divides D. Also, mod of C equal to C is less than or equal to mod of D is equal to D. Why? Already we have seen, if A divides B and B is non-zero, then mod of A is less than or equal to mod of B. This is we have seen. By using this, mod of C is equal to C is less than or equal to mod of D is equal to D. So that D is the greater than every positive integer or more or common divisor of A and B. That is what? By definition of GCD, D is the GCD of A and B. Thank you.